In this video, we will derive the formula for the variance of a frequency-severity distribution by first deriving the formula for the law of total variance. Let's get started. You are given the following information about a Poisson process. Claims occur at a rate of 4 per month. Each claim is independent and takes on values with probabilities below. 25% 5, 50% 50, 25% 95. The monthly claim experience is independent. X is the aggregate claim amount for 12 months. Calculate the variance of X. First thing I want to say for this problem is to read carefully or slowly or reread. I definitely solved the whole problem assuming that the variance of X corresponded to just the variance for claims in a month, not for a year, as it states clearly right there. So just one of those things. It's good to make sure you're paying attention fully while you're reading the question and not skimming too quickly. Thankfully, I was able to not have to redo the problem because of just the way it's all framed, and the memoryless property of Poisson saved me. So we'll get to that eventually. For required knowledge, there's two separate formulas you can choose to memorize. If you prefer to have everything memorized that you could possibly need, then you want to know this first one. So for the specific case of frequency following a Poisson distribution and then severity following something else, it's just the variance of that compound distribution is going to be lambda t times the expected value of x squared. However, I choose to, when I study, try to have the minimal number of formulas I need to have memorized. And so I actually don't bother with this formula. I just know the general form for a compound frequency severity. So that is the variance of the compound frequency severity is the expected value of the frequency times the variance of the severity plus the expected value of severity squared times the variance of frequency. At this point, these two formulas are really all you need to know, and if you're just trying to memorize what you need to know and then apply it, feel free to skip ahead to the actual solution. But for the rest of this required knowledge section, I wanted to step into actually deriving this, and that's because it's used in quite a few videos, and I figured it's worth taking the time to actually walk through it a bit. So to start off, we're just going to say we have the variance formula here. So the variance of y is equal to the expected value of y squared minus the expected value of y squared. And then I'm just reordering so that way I have the expected value of y squared by itself on the left. Next, we have the law of total expectation. So I had to end the rabbit hole at some point, so I chose to just take this for granted and not derive it. So this is, if you have expected value of something, you can pick any other possible variable that you could choose, include it as a given, so the expected value of y given that, and then if you wrap it in another expected value, it's like they cancel. So for example, the expected value of y, let's say y is height. If you said the expected value of height given weight, that's obviously going to change things, right? If I know someone weighs 200 pounds, they probably aren't only 4 feet tall. However, if you wrap that in an additional expected value, then what that is doing is saying, okay, we're going to take the expected height given your weight, but we're going to also take into consideration all different possible weights. And obviously that would be the same as just taking the expected value of height directly in the first place. So that's the law of total expectation. If you are interested in the derivation of that, just Google searching this, going to the Wikipedia page. I believe they have a proof for the discrete case. So feel free to look that up if you're interested. But we're just going to take it for granted. So moving forward, we're going to, again, we have our variance calculation here. And all we're going to do, so I just have that rewritten, and then we're going to wrap that in the expected value. So put all of this in an expected value. And then within those other things, add a given x. And x can be anything we choose. And because of the law of total expectation, that's not changing anything. So at this point, let's see, what do we do here? I think I just rewrote this right section on the left because I wanted it over there. And then, just that since this is addition, we can break the expectation up into its two components. So here I'm just breaking it up into two parts just to make them more distinct. We then are going to subtract from both sides this quantity. And the reason we're doing that is we want to simplify this to be a variance. So jumping ahead, we're going to end up with the variance of the expected value of y given x. And if you treat this whole mess inside as x, variance is just expected value of x squared minus the expected value of x squared. And so we chose to subtract off what was needed to then make this simplify to a variance calculation. So that's why we're subtracting this quantity off from both sides, because that simplifies this. So in doing that, we can rewrite this right section as the variance formula. But then what we also do is we say, hey, it's this double nested expected value. So, we now can take the law of expectation again, total expected value, messing up, law of total expectation. Apply that here, because again, we have a double nested expected value. And so the fact that there's a given x actually doesn't matter, and we can just say it's the expected value of y squared. And the beauty in doing that is we now see, hey, once again, we get a variance formula. And so that just simplifies to be the variance of y. And that is how you derive the law of total variation. So we know that the variance of a variable is equal to the expected value of the variance of that variable given anything else of interest, call it x, plus the variance of the expected value of y given that x. So next, scrolling down some more. So I'm zooming out so we can just see that whole mess. So we care about the total loss amount. So this is a total loss amount can also mean someone didn't have a loss at all, so their total loss amount is 0. So the variance of that is equal to, and then we're just rewriting this formula above, so the total loss amount, and we're going to, again, x could be anything you want. We're choosing to have it be the loss frequency. So given how many losses that policy has, it could be 0, it could be 3, it could be whatever. And then I'm just rewriting it here so that way it actually fits and I don't need to be so far zoomed out. So T just means the total loss amount and F means the frequency. And then eventually you'll see we have this S, which is going to be our severity component. So starting with the left half, and actually only part of it, we're going to ignore this expected value here. So just what is the variance of the total loss amount given the frequency? Well, that's going to be the variance of, well, what's the total loss amount for a given policy? It's just going to be how many accidents occurred, and each of them are going to be of size severity, whatever that is. We also know that, so just rewriting this out as addition, we could then break it up into its different components. And our severities are going to be independent and identically distributed. So that's just one of the assumptions of using that formula that we're in the process of deriving, is that's the case for both frequency and severity. And so we can just split this out, and that's just going to be, so we have the summation of all those independent severities, and because they're IID, we can just take the variance of the overall severity distribution and multiply it by F, so the number of claims that occurred. I also started this indexing at 0, where S sub 0 is always 0. So in the event that you don't have any accident or claim, this would just be amount 0, and that makes sense, right? If you have no claim whatsoever, then the variance of your claim amount is going to be 0. But in other cases where there are claims, then you could start I at 1 if you wanted to. So anyhow, we have the variance of the total loss amount given frequency is just the frequency multiplied by the variance of the severity. So scrolling back up, we now are going to look at the expected value of the total loss amount given the frequency. And this is pretty straightforward, so we're going to have, so this is where we're at. the expected value of the total loss amount is going to end up being whatever the severity is, and we're summing it up across all the different losses or claims. What's the expected value of that? Again, because it's IID, they're all going to have the same expected value, and so that's the same as just taking the expected value of the severity distribution and multiplying that by the number of claims that occurred. So putting that all together, those two things that we solved for were inside the expected value and variance formula. So it's the expected value of, and then the variance times the variance of S times the frequency plus the variance of what we just solved for here, frequency times the expected value of severity. So now what we can do is the frequency and severity are going to be assumed to be independent, and that's just, we can, oh, sorry, that's not what we need to do. Here is the variance of severity, because where frequentist is just a constant, so constants can just be pulled out of this expected value, and so that's why they're split apart here. And then in this case, F can also, the expected value of severity is a constant, but when you pull constants outside of a variance calculation, you need to square it, and that's why this expected value of S ends up getting squared. And that is how you derive the total variance calculation, or formula for a frequency-severity compound distribution. All right, so now we can jump into the problem at hand. So just, again, copying what we just derived, that variance calculation. We know that the expected value of the frequency is 4 because that's what our lambda is, and also for Poisson distribution, the variance is equivalent to the expected value, so again, we just have that 4. I will say at this point, if I had done the problem correctly or read more carefully, the first thing I would do would be to convert this to the annualized frequency. So that would just be 4 times 12, and the variance would then also be 4 times 12. But I did it wrong and then was able to kind of save it on the back end, so we're just going to keep going through this way. So we have then what is the expected value of the severity, and that is the probability weighted average of all possible values. So 25% of the time there's a severity of 5, 50% of the time 50, 25% of the time 95, and then we see the average is just 50. Next, for the variance calculation, we are going to do the exact same thing, but except we care about the expected value of x squared. And so probability weighted average of x squared instead of just x, and then subtract off the mean squared. So just minus that 50 squared that we just solved for. And then that is equal to 1012.5. I had to zoom out to see it because it's such a long mess. So now what I did was calculate the variance, and unfortunately I have a subscript m here because, again, I did it for a month, and so that's just plugging and chugging for this formula. So the expected value of our frequency multiplied by the variance of our severity plus the expected value of our severity squared multiplied by the variance of our frequency. And all of that is equal to 14,050. At this point, I scrolled up, I looked at the solution, and saw I was wrong. But also, if I didn't have the solution, that's a really small number, pretty far away from the boundary of A. And so that would right away kind of be a hint to maybe reread the problem or double check. A little meta advice for if you also do problems wrong like I do. So now, realizing that's the case, the months are independent, Poisson's memoryless, and we can really just multiply this by 12 because the variance of the month 1 and the variance of month 2 are independent, and so their total variance is just going to be the sum of their each of their variances. And so that's just the variance of a month multiplied by how many months we care about, which is 12. And that is another way of getting at the answer of 168,600. Again, we could have just saved that effort by converting our Poisson to be annualized instead of monthly at the beginning to save ourselves that step. So, scrolling up, we see that the solution is E. Let me know you want me to continue making these types of videos by subscribing or commenting below. As always, thanks for watching.